Hello friends. So today we are going to discuss questions of the modern physics. And these questions are from the year 1992. Two questions. 1993. Two questions. 1994. Four questions. And from year 1995, one question. So in totality, we are going to discuss 9 questions. So the first question, it was asked in the year 1992, and it states that when a monochromatic point source of light is at a distance of 0.2 meter from a photoelectric cell, the cutoff voltage and the saturation current are respectively 0.4 volt and 18 milliampere. If same source is placed 0.6 meter away from the photoelectric cell, then we have to suppose to find out the stopping potential as well as the saturation current. So we are given two distances. First distance is our 0.2 meter, second one is our 0.6 meter. So we can say that our initial distance let us suppose we call that as D1. Then our D1 is 0.2 meter, and we are having a final distance that is our D2, and that is our 0.6 meters. And we are also given initial cutoff voltage as well as the saturation current. So we are given initial our stopping potential and initial stopping potential is our, let us suppose, Vs 0.6 volt, and we are having our saturation current let us call this as Is, which will be equal to 18 milliampere. So first we are supposed to find out the stopping potential, and in this case the only thing that is varying is our distance, okay, or we can say intensity. But stopping potential is only dependent upon the, you can say, frequency or energy of the photon. So we can say that our stopping potential depends on only on frequency, or we can say energy of photons. not on intensity or distance. Intensity, or we can say distance. So therefore the value of stopping potential is going to remain unchanged. So we can say our stopping potential will be same, that is our Vs 0.6 volt. So therefore option number B is correct. Option B is correct. And our saturation current is inversely proportional to the square of the distance. So we can say that our saturation current depends upon number of photoelectrons emitted. Saturation current depends on number of photoelectrons emitted, and which is proportional to the intensity of light, which is proportional to intensity of light, and intensity is, suppose I, then this I is inversely proportional to the square of the distance. So we have two distances, so we can divide, or rather write this equation as intensity I2 divided by intensity I1 will be equal to d1 upon d2 whole square. d1 and d2 we know that is 0.2, and we have this is 0.6 whole square. So from here we get our I2 upon I1 will be equal to 1 upon 9. So this gives us that of I2 is equal to 1 upon 9. Value of I1 we know is our 18 milliampere. So this comes as 2 milliampere. So therefore 2 milliampere, option D is correct. Option D is correct. Next question. It was asked in the year 1992, and it states that light from a discharge tube containing hydrogen atom falls on the surface of a piece of sodium. The kinetic energy of fastest photoelectrons emitted from the sodium is 0.73 electron volt. The work function for the sodium is 1.8 electron volt. Find. So based on this we are having 4 questions. First one is the energy of the photon causing the photoelectron emission. Part B, quantum numbers of two levels involved in the emission of these photons. Part C, change in the angular momentum of the electron in the hydrogen atom in the above transition, and the recoil speed of emitting atom assuming it to be at rest before transition. The ionization potential of the hydrogen is 13.6 electron volt. So we are given that kinetic energy of the sodium is given to us. Kinetic energy of photoelectrons is given. So we can write that our kinetic energy of photoelectrons that is given to us as 0.73 electron volt. Work function of the sodium is given, that is our work function, that is our phi is 1.82 electron volt, and finally ionization energy of the ionization energy of the So ionization energy, it is given, let us suppose that is our E1 is our 13.6 electron volt. So in the first part we are supposed to find out energy of photon causing the photoelectron emission. So we can say that energy of incident photons suppose that is given as E, or let us call this as E incident, will be equal to kinetic energy plus work function. So we substitute the value, we get our incident energy of the photon, kinetic energy is 0.73 plus function is 1.82, this gives us 2.55 electron volt. So this was our part A. Now we come to the part B. And in part B, we are supposed to find out the quantum number of two levels involved. So we know that the photons having a energy of 2.5 electron volt is emitted by transition between two hydrogen energy level. And the standard formula of energy level, photons we already know, sorry, not photon, but energy levels of hydrogen we know. Okay. And we are going to make a comparison between that energy equation or values being calculated from the energy equation and with this energy of the incident photon. So based on this we can just write that photon of 2.55 electron volt is emitted by a transition between two hydrogen energy level. Between two energy levels, and equation for the energy level is already known to us, so we can say that energy level equation, which is our for nth level, is equal to minus 13.6 divided by n square electron volt. So we are going to put various value of n. So let us put first value of n is 1, which gives us E of 1 is equal to minus 13.6 upon 1. This gives us minus 13.6. Next, we can take value of n is equal to 2, which gives us E of 2 will be equal to minus 13.6 upon 4. This gives us minus 3.4 electron volt. And next we can take n is equal to 3, which gives us E3 minus 13.6 upon 9, and this comes as minus 1.51 electron volt. And next we can take value of n is equal to 4, giving us E of 4 will be equal to our minus 13.6 upon 16. This gives us minus 0.85 electron volt. And from here we are going to subtract all these energy levels, which basically means we are going to subtract our E2 minus E1, we are going to subtract our E3 minus E2, E3 minus E1, as well as E4 minus E2, E4 minus E3, E4 minus E2, and as well as E4 minus E1. Okay, and from there we are going to get the value. So I will just come directly to the solution, which tells us that if we minus E4 minus our E2, which comes as our minus 0.85 minus of minus 3.4, this gives us 2.55 electron volt. So it means the quantum numbers that are involved are our value of n is our 4 and another value of n is our 2. So we can say that the quantum numbers involved are 2 and 4. So we can say the transition will be our from n1, which will be 4, to our n2, which will be our 2. So this was our part B. Part C, we are supposed to find out the change in angular momentum. Part C, we are going to find out the change in angular momentum. The standard equation for angular momentum is nh divided by 2 pi. And we have two values of n. One is our 4, another one is 2. So we are going to find out that J2 as well as J4. and subtract them. So we can say angular momentum given as J is equal to our NH upon 2 pi. First value of N, that is our 4. So we can say our N1 is equal to 4. So based on this we can say our J1 will be equal to 1 H upon 2 pi. And second value of that is N2 is our 2. This gives us a J2 is equal to 2H upon 2 pi. And this 2 and 2 cancel out. So from here we get this as H upon pi. And we are supposed to find out change in angular momentum. Change in angular momentum, let us call this delta J, will be equal to J1 minus J2. So we can say our delta of J is equal to J1 is H upon 2 pi minus H upon pi. This gives us that the change in angular momentum will be equal to H upon pi. And finally we have part D, which talks about the recoil speed of emitting atom, assuming it to be rest before transition. For that we are going to use our, you can say, conservation. Recoil momentum of the atom will be equal to momentum of the emitted photons. So we have our part D. We are going to use conservation of momentum. Conservation of momentum, which gives us that recoil momentum of atom will be equal to momentum of emitted photons. So recoil, suppose, is given as P, then this P will be equal to our E upon C. Energy we already calculated, that is our 2.55 into 10, sorry, we have to convert into electron volt. So this will be 1.6 into 10 to the power minus, not electron volt, but into our joules, 19, and C is our 3 into 10 to the power 8. So this gives us that the momentum is 1.36 into 10 to the power minus 27. We are supposed to find out a velocity, so which we can do easily. So we can say our velocity V will be equal to momentum divided by mass, and this comes as 1.36 into 10 to the power minus 27. Mass is 1.67 into 10 to the power minus 27. So velocity comes approximately as 0.81 meter per second. Next question. It was asked in the year 1993, and it states that a star initially has 10 raised to the power 40 deuterons. It produces energy via the process, and it is given as 1s2 plus 1s2, giving us 1s3 plus a proton, and 1H2 plus 1H3 is giving us 2He4 plus 1 neutron. If the average power radiated by the star is 10 to the power 16 watt, the neutron supply of the star is exhausted in a time of the order of the mass of the nuclei is for H2, neutron, proton as well as helium is given to us. And so basically it is involving two reactions, or we can say two fusion reactions. So we can say two fusion reactions are, so our first fusion reaction is our H12 plus H12. This gives us H13 plus a proton which is 1:1. And we are having a second which gives us H12 plus H13, giving us a helium-24 plus a neutron which is of 0:1. So in these two reactions we can clearly see a total of 3 neutrons are consumed. So we can say that this is one cycle. Okay, this entire thing is our one cycle. So you can see in one cycle three neutrons are consumed. Therefore, neutron used per cycle is 3. That was our, okay, it's not required, sorry. So we can say that neutrons per cycle, neutrons used per cycle neutrons used per cycle is 3, and total number of neutrons are given. So from there we can find out number of cycles that are possible. So we can say our number of cycles, suppose that is given as small n, will be equal to total number of neutrons and divided by neutrons used per cycle, that is about 3. So this comes as 10 to the power 40 divided by 3. So we get that total number of cycle, that is our n, is equal to 3.33 into 10 to the power 39. Now we are supposed to find out the time period, or we get given the average power. Okay, so based on this we are going to use the mass defect in order to find out what will be the energy, and then we are going to use the relationship between energy and power to get the time. So we are going to use our mass defect per cycle, and which is nothing but our energy released. Energy released. So we have they use are 3 neutrons. So we can say our initial nuclei which is our 3 neutrons, and we are going to get the mass of 3 neutrons will be over 3 into 2.014, and this comes as 6.042 AMU. And our final nuclei we are having one proton whose mass is our 1.007 AMU. We are having one neutron whose mass is our 1.008 AMU, and we are having one helium whose mass is our 4.001 AMU. So therefore total final mass will be equal to 1.007 plus 1.008 plus 4.001, and this comes as 6.016 AMU. Now we can easily find out our mass defect, that is delta M. Mass defect, our delta M will be our initial mass 6.042 minus 6.016. This gives us 0.026 AMU, and this we can easily convert into joules. So we can say our energy, let us suppose that is our E, will be equal to 0.026 multiplied by 931.5 multiplied by 1.602 into 10 to the power minus 13. So we get our energy is equal to 3.88 10 to the power minus 12 joules. So this was energy for only one cycle. Number of cycles we have already calculated. So we are going to find out energy for all the cycles. So you can say total energy for all cycles from all cycles, let us call this as E total, will be equal to our number of cycles multiplied by energy per cycle. Let me write it here, energy per cycle. Number of cycles is our 3.33 into 10 to the power 39. So this comes as 3.33 into 10 to the power 39 multiplied by 3.88, and into 10 raised to power minus 12. So we get our total energy is approximately equal to 1.29 into 10 raised to power 28 joules. So this is our total energy, and we need to find out the time. Power is given to us, so we can say that our time to exhaust at given power, let us suppose that time is our T, that will be equal to our energy total divided by power P. Energy total is our 1.29 into 10 raised to power 28, and power P is our 10 raised to power 16. So this comes as 1.29 into 10 raised to power 12 seconds, and it comes as 10 raised to power 12 second, which is our order of, that is C is correct. Option C is correct. Next question. We are sorry. Yeah. So next question. We are given, it was asked in 1993, and it states that a neutron of kinetic energy 65 electron volt collides inelastically with a singly ionized helium atom at rest. It is scattered at an angle of 90 degree with respect to original direction. Given mass of helium atom is 4 times the mass of neutron, ionization energy of hydrogen atom is 13.6 electron volt. And based on this, we are going to find out two things. First is find the allowed values of energy of the neutron and that of atom after collision. Part B, if the atom gets de-excited subsequently by emitting the radiation, find the frequency of the emitted radiation. So here we are having a collision, which is an inelastic collision, and initially we have a you can see helium atom is at rest and a neutron is moving. Okay, so we can just draw an approximate figure for that. So we have a, suppose, a neutron of mass m and a helium whose mass is our 4 times m. So this is the initial direction, and then it states that they collide inelastically. It is scattered at an angle of 90 degree with respect to original direction. So original direction, suppose this is our x and this is our direction y. So obviously mass m is going to move perpendicularly, that is along the y direction. So we can say this is our helium and this is our neutron, and this neutron will try to move in this direction. Let us suppose its kinetic energy is K1 and our helium is suppose moving in other direction, which is suppose a kinetic energy of K2. So we are just going to use the conservation of momentum in x direction, and suppose let me draw this with respect to close to x-axis. Okay. So suppose it is moving in this direction, that is our k2, and the angle is given as theta. So our k2 can be divided into two components. This will be k2 sine of theta, and along this axis we are going to get k2 cos of theta. And we are going to use conservation of momentum along x-axis. And initially the helium was stationary, so velocity was 0, and we are given neutron is moving with some kinetic energy. Let us suppose that kinetic energy is k. Therefore we can say that conservation of linear momentum along x-axis, we can write our initial momentum P initial is equal to P final. So initial momentum will be only associated with our this neutron because our helium is at rest. So in terms of kinetic energy, that will be coming as 2 km and square root, and we are taking x-axis, so therefore the initial momentum of neutron will be 0 along x-axis, and along for our this helium, that will be our 2 4 times m, and this will be our k2 cos of theta and its square root. Similarly, conservation of momentum along y-axis, along y-axis, and the initial momentum along y-axis is 0. So let me rephrase it. This is a p of I in x, p of f in also x, and here also p of in y, and this is over final along y, and initial along y is 0, so this comes as 0 is equal to, and we are having our, let us suppose we define our axis, so this is our x-axis and our y-axis. Okay. So final momentum of our neutron will be equal to our 2 k1m square root minus, because it is along negative y-axis, it comes as our 2, and this is 4 times m k2, and we have our sine of theta and its square root. So we can just equate or rearrange this equation. We get this as 2 k1m square root is equal to 2 4m k2 sine of theta and its square root. Okay. And let us call this equation number 1 and equation number 2. So we square and add equation 1 and 2. Squaring and adding equation 1 and 2. So from there we can write that our 2 km plus 2 k1m is equal to, we get this as 8 k2m 1 second. And 8k2m sine square theta and cos square theta. Sine square theta plus cos square theta. And we can cancel our this mass, and 2 also goes by 4. So we get this as k plus k1 is equal to 4 times k2. Or we can write this equation as 4 times k2 minus k1 is equal to k, which is ever given to us as kinetic energy of neutron is 65 electron volt, is equal to 65 electron volt. And one second. Find the allowed values of energy of neutrons and that of atom after the collision. Okay. So because of the collision, the electrons will be, you can say, excited to high energy state, and for that we are going to use conservation of energy. So we can say during collision electrons can be excited to any higher energy state. So conservation of energy, conservation of energy, we already know the equation for our energy which we just found out. So we can say that our initial energy, that is our kinetic energy only, will be equal to energy of neutron after collision plus energy of the atom after the collision plus the energy that will be released. And value of k we already know is our 65 electron volt. And we are supposed to find out what will be the possible values of our delta E. So we can say that our k1 plus k2 one second. Mass of this, okay. So we can let us suppose that the possible value of delta E, it can be written as our delta E1 will be equal to minus of 13.6 minus of minus 54.4, which gives us 40.8 electron volt. For that, okay, let me first draw the energy level, and that will be much more convenient to understand, because this value we can easily find out by using our energy level. So this is our value of n is equal to 1, and this is our value of n is equal to 2, and then we have a value of n is equal to 3, and finally we have value of n that is equal to 4. And all these transitional values we already know, and we are given that it is helium whose value of Z is given as 2 rather. So from here we get this value of minus 54.4 electron volt. For value of n is equal to 2, this will be minus 13.6, this will be minus 6.04, and this will be minus 3.4. And we can also draw the transition, so this will be between 1 and 2, 1 and 3, and we are going to have 1 and 4. So therefore the possible value of delta E is our 40.8 electron volt. So if we use our equation, that is let me name the equation, let us call this as equation 1 and this as equation 2. So we found out our delta E. So using equation 2, from equation 2 we get K1 plus K2 will be equal to 65 minus delta E. Delta E1 in this case, and we get this 65 minus 40.8, and this will be coming as our K1 plus K2 will be 24.2 electron volt. And now we have two equations, equation number 1, and let us call this as equation number 3. So from equation 1 and 3, from equation 1 and 3 we can easily find out our K1 and K2, and equation 1 is our 4K2 minus K1. 4K2 minus K1 is equal to 65, and we have here K1 plus K2 is equal to 24.2. So if we add them, this K1 cancel out, so we get this as 5 times K2 is equal to, this will be coming as 0.2, and here we have 9, and here we have our 89. So this gives us that our K2 will be equal to 17.84 electron volt. Similarly, we can find out our K1, and that will be coming as 6.36 electron volt. And similarly, we are going to find out our delta E2 also, because that is going to give us another value of K1 and K2. So we can say similarly, we can say our delta E is suppose our delta E2, and which gives us 0.064 minus 0.6 minus of minus 54.4. So from here we get our delta E2 will be equal to 48.36 electron volt. Similarly, we are going to find out our K1 and K2, which we just found out. So let me write the results directly. So from here we get our K1 will be equal to 0.312 electron volt, and value of K2 is our 16.328 electron volt. And similarly, we are going to put delta E is equal to delta E3. Delta E is equal to delta E3, and which gives us minus 3.4 minus of minus 54.4, and we get our delta E3 will be equal to 0 electron volt. So based on this delta E3, we are going to get another set of K1 and K2. We get K1 is equal to minus 1.8 electron volt, and we get our K2 is equal to 15.2 electron volt. Okay. So which basically means, because for this particular value of our delta E, we found out that one of the value of the kinetic energy is negative, which is not allowable. Okay. So means that, which basically means that electron will not jump to third excited state. You can say that electron will not jump to third excited state, or we can say value of n is equal to 4. So therefore, the allowable values of K1 allowable values of K1 will be equal to our 6.36 and 0.312. K1 are 6.36 and 0.312 electron volt, and that for K2 we are going to have our 17.84 and 16.328 electron volt. And From here we can also say that electron can jump only up to second excitation state, that is value of n is equal to 3. Electron can jump up to second excited state, or we can say value of n is equal to 3. Next, it is asking that if the atom get de-excited subsequently, find the frequency of emitted radiation. So for part B, our electron is de-excited and value of n is equal to 3. So this is our value of n for 3, value of n is equal to 2, and we have value of n is equal to 1. So which basically means from 3 it is going to de-excite to our value 2, and it can also de-excite it directly to value of n equal to 1, or it can from, so this will be our 1, 2 as well as 3. So we can easily find out the corresponding frequencies. And let us call this as our F1 is equal to our E3 minus E2 divided by H, and we get this as minus 6.04 minus of minus 13.6, and converting into joules 1.6 into 10 to the power minus 19, and divided by H, which is 6.6 into 10 to the power minus 34. So we get our value of F1. First frequency is 1.82 into 10 to the power minus, sorry, not minus, plus 15 hertz. Next is for between 3 and 1. Let us call that as our F2. So our F2 will be equal to E3 minus E1 divided by H, and we get this as minus 6.04 minus of minus 50.4 into 1.6 into 10 to the power minus 19, 6.6 into 10 to the power minus 34. So we get our F2 is equal to 11.67 into 10 to the power 15 hertz. And finally between second and 1, so let us suppose that is our F3. So we have our F3 is equal to E2 minus E1 upon H, and we get this as minus 13.6 minus of minus 54.4 into 1.6 into 10 to the power minus 19, 6.6 into 10 to the power minus 34. So we get from here that our F3 will be equal to 9.84 into 10 to the power 15 hertz. So these three are the values of the frequency values of the emitted radiation. Next question. It was asked in the year 1994, and it states that consider alpha particles, beta particles and gamma rays, each having an energy of 0.5 mega electron volt. In increasing order of penetrating powers, the radiations are. This is quite straightforward. You can say the initial energy given to alpha, beta and gamma is same, and the order will be for our alpha particle is less than our beta is less than our gamma. Okay, so this will be basically our order, alpha, beta and gamma. So option A is correct. Option A is correct. And basically if we want to, you can say, draw the discussion on this, we can say that our alpha is the heaviest particle and it is highly you can say ionizing, so that's why it's the least penetrating. And our beta particle, which can be of electrons or we can say positrons, so they have the tendency to be moderately ionized, so they have a moderate penetration. So basic comparison we can draw between our alpha as well as gamma. Beta is going to lie somewhere in between, and our alpha and gamma are the opposite end of the spectrum. Okay. And because they have no mass as well as no charge, so they have a high penetration power. Okay. Because there is, you can say, from any nuclear, you can say if there is a charged body, then our this gamma is have the maximum tendency to pass. Okay. So this is in general discussion, not a very, you can say, detailed one is required there. Next question. It was asked in the year 1994 and it states that when photons of energy 4.25 electron volt strike the surface of metal A, the ejected photoelectrons have maximum kinetic energy Ta expressed in electron volt and De-Broglie wavelength as lambda A. The maximum kinetic energy of the photoelectrons liberated from another metal B by the photons of energy 4.70 electron volt is Tb is equal to Ta minus 1.50 electron volt. If the De-Broglie wavelength of these photoelectrons is lambda b, which is equal to twice of lambda a, then we have to find out the work function and we are going to find out their kinetic energy for their respective things. And here we already know the formula for our De-Broglie wavelength and the kinetic energy. So we can say our De-Broglie wavelength, that is our lambda, is equal to h upon 2m square root of k. And from here we can say that our lambda is inversely proportional to square root of k. And we have two metals A and B and their respective energy is given to us. Okay. So we have our metal A and for metal A, photon energy, that is a EA, is 4.25 electron volt and the maximum kinetic energy max is said to be over Ta, and the wavelength, De-Broglie wavelength, is our lambda A. Similarly, we can write that for metal B, we have our energy of EB. Energy of EB is our 4.70 electron volt, and the kinetic energy max, it is given as TB, which is dependent upon TA minus 1.70. And in this case, the De-Broglie wavelength, that is our lambda B, is given as twice of lambda A. So from here we can say that our lambda B upon lambda A is equal to 2, and we already know relationship of our De-Broglie wavelength with respect to kinetic energy. Here kinetic energy is represented as T. So let me write it. Lambda is inversely proportional to square root of T. So lambda A will be equal to 1 upon square root of TA, and this will be equal to our square root of TA divided by TB. So we get that our TA upon TB is equal to 4, giving us TB is equal to TA divided by 4. And we also know the relationship between the T and TB that is given to us. So we can use that relationship, and we can write that our TB is our, let me write it first of all, TB is equal to TA minus 1.5. So we substitute value of our TB is our TA upon 4 is equal to TA minus 1.5, and this gives us our TA is equal to 4 times TA minus 6, and from here we get our 3 TA is equal to 6, giving us TA is equal to 2 electron volt. Now we can easily find out our TB. So we can say our TB is equal to TA by 4, that is 2 by 4, which gives us 0.5 electron volt. And we are supposed to find out the work function. Energy we also know the this kinetic energy as well as the photon energy. So we can say work function for metal A let us suppose we are given that phi A will be equal to energy of photon minus kinetic energy, and we substitute the value. We get this as EA is our 4.25, TA we found our 2, this comes as 2.25 electron volt. So work function for A is 2.25 electron volt. So option A is correct, and energy for TA is 2, TB is 0.5, so this is wrong. And work function for B, so we can say metal B, work function is our phi B is equal to our EB minus TB, which gives us 4.70 minus 0.5. So we get our phi B is equal to 4.20 electron volt. So our phi B is also correct. So option A, B, C are correct. Option A, B and C are correct. Next question. It was also asked in the year 1994, and it states that a hydrogen-like atom, atomic number Z, is in a higher excited state of quantum number n. The excited atom can make a transition to the first excited state by successively emitting two photons of energy, 10.2 and 17.0 electron volt respectively. Alternately, the atom from the same excited state can make a transition to second excited state by successively emitting two photons of energy, 4.25 electron volt and 5.9 electron volt, 95 electron volt respectively. Determine the value of N and Z. Ionization energy of hydrogen atom is given as 13.6 electron volt. So we are given that successive photons are emitted in both the cases, but how they are emitted is different. So they have two paths in which the we can say energies are being emitted. So we can say that two paths of successive photon emission two paths of successive photon emission from same excited initial state is same in both cases. Photon emission from same excited state. To different lower states. To different lower states. So let us call first path as P1 and second path as P2. So we have a path 1 which we are calling as P1, and P1 is for our first excited state. So you can say P1 to first excited state. So we have two energy level. Let us call this as E1, which is 10.02 electron volt, and we have our E2, which we call as 17.0 electron volt. So therefore we can say the total change in energy total change, or we can say total energy change rather, will be equal to 10.2 plus 17, which gives us 27.2 electron volt. Therefore we can write that if it jumps from our a certain nth energy level, then minus our E2 will be equal to 27.2 2 electron volt. Okay, because it is a first excited state, which gives us that the value of n will be equal to 2. So let us call this as equation number 1. Similarly, we can find out equation number 2, that is for path 2. Path 2, let us call this P2, and this is 2 second excited state, which gives us that the value of n is equal to 3. And we can call this as E1 prime will be equal to 4.25 electron volt. E2 prime is equal to 5.95 electron volt. So total energy change will be equal to 4.25 plus 5.95, giving us 10.2 electron volt. Therefore, we can write the equation that from nth level to our third level, the difference will be our 10.2 electron volt. So this is our equation number 2. So if we subtract equation 1 and 2, subtracting equation 2 from 1, we can write this as En minus E2 minus En minus E3, which will be giving us E3 minus E2 will be equal to 27.2 minus 10.2. So from here we get our E3 minus E2 will be equal to 17.0 electron volt. And we already know that the basic formula for nth energy level, you can say that energy level of hydrogen like atom, it is our E of n is equal to minus 13.6 z square upon n square, and value of n we already know is 2 and 3. So we can say that for value of n is equal to 2, we can find out our E2 will be equal to minus 13.6 z square divided by 4, and for n is equal to 3, we get our E3 will be equal to minus 13.6 divided by 9, and we have z square. So we substitute these two value, or we can say we write E2 minus E3 minus E2, E3 minus E2, we can take common as minus 13.6 z square, and we have this as 1.9 minus 1.4. This gives us 13.6 z square and multiply by 5 by 36, and this difference is already known to us, that is our 17. So we substitute it, we get our 13.6 z square multiplied by 5 upon 36 is equal to 17. So from here we can write that our z square will be equal to 17 into 36 divided by 13.6 multiplied by 5, and this comes as equal to 9, or we can say value of z is equal to 3, which we were supposed to find out, value of n as well as z. Okay, we are supposed to find out value of n. We already found out value of z. And we already know that E of n minus E of 2, any equation we can use. E of n minus E of 2 is equal to 27.2 electron volt, and E of 2 we can write from the standard equation is minus 6, and value of z is 3, so this comes as 9 divided by 4. So we substitute it, we get our E of n is equal to 27.2 plus, and we have our E of 2 is minus 13.6 into 9 divided by 4. And this will be equal to minus 13.4 electron, minus 3.4 electron volt. And for E of n, we can write this as minus 13.6, z square we know is our 9 divided by n square is equal to minus, this is 3.4. So our minus and minus cancel out, this we have multiplication, and we get value of n square will be equal to 13.6 multiplied by 9 divided by 3.4, which gives us 36. Therefore value of n is equal to 6. Next question. It was asked in the year 1994, and it states that a small quantity of solution containing Na24 radionuclide, half-life 15 hour, of activity 1 microcurie is injected into the blood of a person. A sample of blood of volume 1 centimeter cube taken after 5 hours shows an activity of 296 disintegration per minute. Determine the total volume of blood in the body of the person. Assume that radioactive solution mixes uniformly in the blood of the person. 1 curie is 3.7 into 10 to the power 10 disintegration per second. Okay. So here we are going to find out the total volume assuming the uniform mixing, and we are given half-life of Na24. Let us suppose that is our half-life of Na24, that is our T half, it is given to us as 15 hours, and initial activity is given to us 1 microcurie. So we can see initial activity let us suppose that is our A naught, will be equal to 1 microcurie, and this will be equal to, in terms of disintegration per second, will be 1 into 10 to the power 6 curie multiplied by 3.7 into 10 to the power 7 10 to the power 10 disintegration per second. So we get our A naught will be equal to 3.7 into 10 to the power 4 disintegration per second, and we are given that the sample is taken after 5 hours. Okay. So it means value of T is 5 hours. So we can say that time after injection that is value of T is our 5 hours, and activity that is measured at this time is given as 296 disintegration per minute. So which we are obviously going to convert to per second. So you can say activity measured in a 1 centimeter cube blood. Let us call this as A sample will be equal to, given as 296 disintegration per minute, and this comes as 296 divided by 60, which is approximately 4.93 disintegration per second. And the standard formula, that is our decay law, we can use directly. So we can say decay law, it gives us that activity A will be equal to initial activity e raised to power minus lambda t, where lambda is our decay constant. So we can just find out that lambda is equal to natural log of 2 and divided by t half, which is 0.693. T half is our 15, giving us 0.0462 per hour, and T is given to us as 5 hours. So therefore we can say our A will be equal to A naught we found out as a 3.7 into 10 raised to the power 4 into e raised to the power, this is minus 0.0462 multiplied by 5, and this our A can be approximated as 2.94 into 10 to the power 4 disintegration per second. And we are going to find out the volume, because this activity is our total activity, and we are also given activity per volume, okay, that is per centimeter cube. So we can say that volume V will be equal to total activity divided by activity per centimeter cube. Activity per centimeter cube. So we already know that our total activity we found out is 2.94 into 10 to the power 4, and per volume is given as 4.93, which is approximately equal to 5962 centimeter cube. In terms of liters, we can write this as 5.962 liters. Next question. It was asked in the year 1995, and it states that in a photoelectric effect setup, a point of light power 3.2 into 10 to the minus 3 watt emits monoenergetic photons of energy 5 electron volt. The source is located at a distance of 0.8 meter from the center of the stationary metallic sphere of work function 3 electron volt and of radius 8 into 10 to the minus 3 meters. The efficiency of photoelectron emission is 1 for every 10 to the power 6 incident photons. Assume that the sphere is isolated and initially neutral, and that photoelectrons are instantly swept away after emission. So based on this, we have 4 questions. Part A, calculate the number of photoelectrons emitted per second. Part B, find the ratio of wavelength of incident light to the De-Broglie wavelength of the fastest photoelectrons emitted. Part C, it is observed that photoelectron emission stops at a certain time t after the light source is switched on y. Part D, evaluate the time t. So first of all, we are going to find out the number of photoelectrons emitted per second. So in part A, we are given that energy of the photon is given to us as 5 electron volt. So we can say energy of the emitted photons let us suppose that is our E1. So we can say our E1 is equal to 5 into 1.6 into 10 to the power minus 19 joules, which will be coming as our 8 into 10 to the power minus 19 joules. And the power of the point source is given. Power of point source that is given to us, let us suppose we call this as P, is equal to 3.2 into 10 to the power minus 3. So we can say energy emitted per second. From the power, we can write that our energy emitted per second, let us call that E2, is equal to 3.2 into 10 to the power minus 3 joules. So therefore, we can find out number of photons emitted per second. Number of photons emitted per second. Let us call this as our N1 will be equal to E2 upon E1. We substitute the values of E2 and E1. So we get N2 is equal to E2 is 3.2 into 10 to the power minus 3, and E1 is 8 into 10 to the power minus 19. So we get our N1 is equal to 4 into 10 to the power 15, and now we are also given that we have a area, the distance is given as 0.8 meter from the source. So based on that, we can say that number of photons incident on unit area at a distance of 0.8 meter from source. Let us call that N2, and this value of N2 will be equal to our N1, and we have this as 4 pi, and distance is 0.8 whole square. So we have our N1 as 4 into 10 to the power 15, and this is our 4 pi into 0.8 whole square. So this comes as approximately as 5 into 10 to the power 14, and we are given that the area of metallic sphere over which the photons will fall. Radius is given, we can find out area. So we can say area of metallic sphere over which photons will fall. Let us call that area as A will be equal to pi r square. So this comes as pi, radius is about 8 into 10 to the power minus 3 whole square, and we get this area is approximately equal to 2.01 into 10 to the power minus 4 meter square, and we found out on the unit area, and we already know value of area. So therefore we can say that the photons will fall, number of photons on area A, number of photons on area A, let us suppose we have this N3, will be equal to N2 multiplied by A. So we get our N3 will be equal to N2 is our 5 into 10 to the power 14 multiplied by 2.01 into 10 to the power minus 4. So we get our N3 is equal to 10 to the power 11. But it is given. Now we found out the number of photons, and we are supposed to find out the photoelectrons, and we are given that for one we are having one photoelectron for 10 to the power 6 incident photon, and we know that the number of photons are 10 to the power 11. So based on this we can find out the number of photoelectrons emitted in 1 second. Number of photoelectrons emitted per second. Per second, that is our N will be equal to, we have our N3, and this is 10 to the power 6. N3 is our 11 and 10 to the power 6, giving us 10 to the power 5 per second. This was our part A. Part B, ratio wavelength, De-Broglie to the fastest one. So we have part B. We can find out the wavelength of incident light based on the energy equation. Okay. So we can say energy equation that of energy E is equal to hc upon lambda, which gives our lambda is equal to hc upon E. And E already we know, so we get our lambda is equal to 6.6 into 10 to the power minus 34. Speed of light is 3 into 10 to the power 8, and energy is our 8.01 into 10 to the power minus 19, which gives us that our wavelength will be equal to 2.48 into 10 to the power minus 7 meters. And from here we can find out our maximum kinetic energy of the photoelectrons. You can say that max kinetic energy, let us suppose that is given as K max, will be equal to our energy minus work function. Energy is our 5 minus 3, giving us 2 electron volt, and converting into joules, we get our maximum kinetic energy is equal to 2 into 1.6 into 10 to the power minus 19, which gives us 3.2 into 10 to the power minus 19 joules. Now we can find out the De-Broglie wavelength. Wavelength lambda g is equal to h upon square root of 2 mass of electron multiplied by kinetic energy, which we just found out. This kinetic energy is maximum kinetic energy. Therefore we can say our lambda g is equal to h is our 6.6 into 10 to the power minus 34, and this is 2 into mass of electron is 911 into 10 to the power minus 31 multiplied by energy 3.2 into 10 to the power minus 19, and its square root. So we get the De-Broglie wavelength will be approximately equal to 8.68 into 10 to the power minus 10 meters. And now we are simply going to find out the ratio. So we can say our ratio lambda upon lambda g. Lambda g is our 8.68 into 10 to the power minus 10, and lambda was our 2.48 into 10 to the power minus 7. This comes approximately equal to 286. And we have part C. It is observed that photoelectron emission stops at a certain time t is switched. We have to find out the reason, and the reason is quite simple, because the sphere will continuously, initially the metal sphere was neutral, but as it's going to start to emit the lose the electron, the sphere is going to get the positive charge, or we can say slowly a positive potential will be built on the sphere, and eventually the positive potential on the sphere will be so high that the photoelectrons will not have enough kinetic energy to escape the sphere surface. So at that particular time, the photo emissions are going to stop. So we can say initially we have a sphere and that sphere is neutral. This is the initial condition, and you can say that sphere loses electrons, or we can say gain positive charge. Or from here we can also say that positive potential builds up on sphere, and because of this this potential becomes high, potential becomes so high that emitted electrons no longer have enough kinetic energy to escape the sphere. And at this particular moment, we can say at this point photo emission stops. At this point photo emission stops, and we need to find out the time t. Okay. And first of all, we can easily find out what will be the maximum kinetic energy of the photon. Now we come to the part D. We can say maximum kinetic energy of photoelectrons, that is our K max. That is a standard equation. We can write our K max will be equal to energy minus work function. Energy is given to as 5, work function is our 3. This comes as 2 electron volt. So it means the photo emission stops when the sphere becomes charged enough for our this maximum greater than equal to this 2 electron volt. So therefore we can say that potential on sphere, that is our V, is equal to 2 volt, because the maximum kinetic energy is 2 electron volt. So it will be greater than or equal to K max. And we need to find out the charge that is required. Charge. Okay, we need to find out the time. For that we require charge, and then we can find out our time. So we can say that charge required to raise potential to 2 volts. So we can use the simple equation that the potential V for the sphere is 1 upon 4 pi epsilon naught. Suppose charge is Q, radius is given to as R. So from here we get our Q is equal to 4 pi epsilon naught multiplied by R times V. And we know all these values, and can say that our charge Q, we have this as 4 pi epsilon naught is our 8.8 pi 4 into 10 to the power minus 12, radius is 8 into 10 to the power minus 3, and potential is 2. So we get our Q, that is our charge, will be approximately equal to 1.78 into 10 to the power minus 12 coulomb. So this is the charge, and from here we can find out the number of electrons required for this charge. Number of electrons for charge Q, that is of N is equal to total charge and charge on one electron. So we get the value of N is equal to 1.78 into 10 to the power minus 12. Charge on one electron is 1.6 into 10 to the power minus 19. So from here we get value of N is 1.11 into 10 to the power 7 electrons. So we found out the number of electrons, and we already know that photoelectrons emitted per second. Okay, that is value of rate basically, and in time t it is going to emit n electrons, that is 1.11 into 10 to the power 7. So finally we can say that emission rate which basically is the time t to emit n electrons. So whichever t is equal to 1.11 into 10 to the power 7 divided by photoelectrons emitted per second, and that per second is given to us as 9.98 into 10 to the power 4. So from here we get our t is approximately equal to 111 seconds. Yes, so this completes all the questions. We solved total 9 questions, and the 9 questions were from the year 1992, 93, 94 and 95. So this completes all these 9 questions. Thank you.